Thank you for the invitation. Thank Gira and Ekla for this opportunity for me. It's really meaningful for me from Hong Kong because this is my first time to stand here to give a face-to-face presentation since 2019. So really thankful and grateful for give this opportunity to me. And first of all, I feel like today is like micromagnetics day. So please allow me to use one presentation a little bit away from the magnetization. I'm talking about stress and strain. So you can think about strain is a gradient of magnetization, and the quadratic form of strain gives the electric energy, and have this kind of analogous. So today I'm going to talk about two-tier compatibility of phase transforming polycrystallized. I highlight polycrystallized most of my previous talk, and maybe Dick Jam is my long-term collaborator. He talked a lot about the compatibility conditions of one-sided phase transformation. Most of the derivation is based on the single crystals. And today, my focus is try to understand the role of grain boundary inside polycrystals and how do we make grain boundary compatible during the stress-induced materials. So here I want to give you an overview of today's talk. First, I would like to do some a little bit of review what previous compatibility conditions are and what's the implications they are used in material development, and try to make the material has very low hysteresis and very highly reversible over very long cycles of phase transformation. And then I would like to highlight something that we maybe didn't pay too much attention about the terminology of the reversibility mechanically and thermally. So in previous years, I mean, people talk about reversibility. People always talk about if we have a piece of material, we heat it up at the free boundary, and then we cool it down. And then we look at the transformation temperature, go forward and backward, and we calculate the hysteresis between the transformation temperatures. We define it as the hysteresis, and there's some conclusion that people can minimize such hysteresis based on the compatibility conditions. And today I'm more talking about stress-induced, when the material under some very well-defined stress boundary condition, and under such kind of boundary condition is the reversibility and hysteresis still related to the compatibility conditions in the same manner. And then I would like to discuss some new things like tier 1 compatibility. What are we going to look at, what kind of material aspects? And then we look at tier 2 compatibility that is related to the grain boundary. And then last, I would like to propose some open questions on some latest experimental discoveries. When we look at the bicrystal, we have one orientation or one grain together with another grain with a different geometry of the grain boundary. What do we look at them, and what's the result of the mechanical driven reversibility, and how does that mathematically related to the tier 1, tier 2 compatibility in the material? And today, since this is discussing the challenges in complex materials, I would like to really show you how complex the real material is and how messy the microstructure in real materials are. So that's my overview. And first of all, I still want to give some very, very applied aspects why we look at these materials. And here, not only the phase transforming metals, I put phase transforming materials. Actually, on your left-hand side, I highlight the mechanically driven reversibility. People call it super elasticity. Super means the material undergo phase transformation when we load it. And then we unload it, the material transforms back to the ultimate, which is the reference configuration, and the deformed configuration, which is the marking site. And those are the applications people want to use the super elasticity, which is really on the stress-induced phase transformation. And on your right-hand side, that's another application of phase transforming materials, maybe metals. People call it shape memory effect. That is, we actually a little bit stretch the material or let the material under a little bit strain, and then we change the temperature. We simply change the temperature, and the material can show the deformation. And deformation can recover back and forth, and people use it as the actuator. Actually, this graph, as you can see, I grabbed it from a really, really old reference. And nowadays, people do not like to use it as the actuator because it doesn't show the linear response. And there are some other materials which is not shape memory alloys, but they still show some very sensitive morphine shape kind of phenomena as the temperature changes. So here, let me play some very interesting application. This is due to the stress-induced phase transformation. When we pull it, it will release the heat, and then when we release it, it will absorb the heat. And at the hot side, people just use some heat sink to get heat away, and then let it to absorb a lot of latent heat during the reverse of the phase transformation, and people use it for the solid state refrigeration. And here, this is just some IR image, just to give some IR signal. The material can morph in the shape back and forth. So this is what we mean by reversibility. We want the material deform reversibly under some external stimulus. It could be the mechanical stimulus, or it could be the temperature stimulus. And how do we evaluate those materials, which is very important here? So we evaluate from two aspects. We want to say, we want the material have a very large transformability, like we want to have a large transformation strain and then can be fully recovered. And we also want it has a high reversibility. So we want to apply such phase transformation like cyclic for many, many cycles. And such kind of transformability doesn't degrade over cyclic transformations. So that's how we evaluate the material. And how do we achieve that? So we can design the material, single crystal, we can design single crystal, and we can design the lattice parameter of the reference phase, austenite, high symmetry one. And we can also design how it transform to. It can transform to tetragonal from cubic. It can transform to monoclinic, even lower symmetry. And during this kind of reversible symmetry breaking transformation, we can calculate the transformation stretch or transformation strain. And that actually underlines the total transformability of the material in a single crystal. And then how do we evaluate and how do we understand the reversibility? So in previous years, people proposed the compatibility conditions for microstructure. In a single crystal, when a new phase, nucleon broke from the reference phase, and they have different crystal structures, there has to form some interface. And this interface, if the lattice parameters is designed exactly right, they can fit together without any elastic transition layer. And we propose if this condition satisfied, the material becomes highly reversible. So that's the previous intuitive thinking. So here I just cite the very old paper from John and Dick James. And if we have a piece of solid, and suppose we have a free boundary condition, it transforms. And some part transformed by deformation gradient F plus, and some part transformed by deformation gradient F minus. At the interface, if they're deferred by rank one matrix, then we say in continuum scale, we say such interface can fit together and there's no interfacial distortion. And by Cauchy-Beaume rule, we find that if we look at the crystal structure, if one side is the crystal structure which is undeformed austenite, it could be some other variant of martensite. And the point is that we have the other side which is deformed, as we can see that the periodicity of the lattice truly changes. This becomes a little bit elongated, and this is like a very good square or cubic. So such a way, we still can make the lattice parameters exactly right so that there exists an interface. solve that equation and we can find such interface so that they form this like atomically sharp interface. And people also observe it in some very special nickel titanium doped with palladium, very delicate doping element that can exactly make the lattice parameters right, so that this kind of atomically sharp interface exists. And then people find, okay, when we make this kind of geometry happen, the real material show very low thermal hysteresis, and the material becomes very highly reversible in terms of like thermal cycles. And here, some like a microstructure implication is that we have a reference austenite. Usually, the lattice parameters cannot genetically satisfy that. But after some like chemical kind of thing make such material satisfy that equation, then this single variant can perfectly fit with austenite lattice and through this very sharp and lattice distortion free interface. Yes.
May I ask you a question? So is it saying that the position of the interface between the two faces is the one that will decide which variant of martensite will take place, for instance, in phase transformation? Because I mean, the shape depends on which variant it chooses, no?
That's a good question. So here, so if we fix this as a undeformed, now the question is what variant of martensite can fit? Actually, if this pure stretch part, we can get rid of this notation. So if we only look at the stretch part of it, actually any variant can fit with austenite, but through different interface normal.
So, yeah, once you have the interface, only one variant is possible.
Normal changes solve the same equation, but interface normal changes. So here, in some real materials, this is the real materials, and people measure the lattice parameters and calculate the equalizing value of the stretch tensor. That is U here. And as we can see here, this one is far away from one, and this one is quite close to one. And then we find this twin laminae here when it's not a perfect interface, and we have elastic transition layer and martensite variant branching into the austenite. And this one is obviously different from that one. This is austenite, and they have a very big martensite single variant. So those are like some results 10 years ago. And here I want to show something not very geometrical, but how do we connect the mathematical condition of compatibility with some realistic property of the materials. So here I only talk about the thermal hysteresis, means we have that piece of material, we only heat it up and cool it down stress-free. And then, as you can see, I present lots of real data here. Each dot correspond to a real materials here. Those data are produced by, this is the simple combinatorial method. So people have a target and people mix different elements at different composition and make a very big disk. At each place, the composition changes, so the lattice parameter changes, and locally the compatibility condition changes. And people directly calculate the thermal hysteresis for each of the composition on that big area. People call it combinatorial experiment. That's the thin film data, and people show that the thermal hysteresis really minimized at lambda equal to 1. I believe Dick James already showed that many times to this community. And here is very interesting. This is a oxide. This is not the alloy. So this material also fabricated by the similar combinatorial method, also thin film. And people also find in this material, it has tetragonal to monoclinic transformation. And also the thermal hysteresis minimized at lambda 2 equal to 1. And here we have some unpublished results, which I don't think it can be published because this was made by a previous postdoc and a PhD student long time ago in University of Minnesota's lab. And after graduation, we still didn't really publish this data, but I think this data is very interesting. So we have this kind of series, and we dope different this like copper, gold, these kind of examples. And this is different from that experiment. This is bulk. So this is a bulk sample made by arc melting. So we really have like this kind of body. And then we cut it, polish it, and measure the lattice parameter, and we find this material also shows the same result as the thin film materials. And also, if we blow up the bottom here, and we find if we do an even finer tuning, I think the published result probably is here at palladium 11. So I think Dick already showed that many, many times. And then DJ, we really made very, very fine tuning. I just slightly change the composition, and we find that it actually can minimize here, even closer to lambda 2 equal to 1. And we also have many other phase transforming materials, some Hussler alloy. This is like ferromagnetic shear alloy. And we have some single crystal. This is a single crystal. And other examples, they're polycrystal lines. And what I want to show here is that the minimal hysteresis is different in each of the material system. Means if the phase transformation type is different, the thermal hysteresis minimum corresponds to different degree. So for example, here it can really reach 2 degrees, but in this material it can only reach 6. And for some of the samples here, it can really reach 0. And for some of the material, you tune the material and try to find the minimal hysteresis by making lambda 2 equal to 1, but the minimal hysteresis may be the 2 digits. So this is interesting. Then we look at it from different aspects. So let's look at nickel, titanium, copper material. So that is the material class line, right? So people still making this material by very fine doping of the copper atomic ratio. So here, this one and this one only differ by 1 atomic ratio of the copper. And we find that this is the which is the differential scanning calorimetry that measures the transition temperature as we heat it up and transition temperature as we cool it down. And the difference is the hysteresis, and we can see that the hysteresis is different. And if we do the thermal cycling, and we find this one actually, the transition temperature migrates, the functionality changes. And this one is exactly on top of the cycle. And then if we make this material on the stress, so this is the stress and the strain curve. If we load it, uniaxial loading, if we load it, and then we'll have the stress-induced phase transformation, achieve the superelastic strain here, that is due to the stress-induced transformation. And then we have martensite here, austenite here. And these two material, the thermally not so reversible material, which has much better stressly induced phase transformation, has much better reversibility in stress-induced phase transformation here. But the thermally more reversible material, which shows very prominent degradation on the stress. And then my collaborator, Eka Kwan, he did a very, very helpful chemical doping by some other element with some very dedicated kind of doping. They find the hysteresis is more or less 15. The lambda 2 is quite close to 1, but each of the material, they have different mechanical reversibility. So now, I really want to ask a question like, is thermally reversible material still reversible if we put it on the stress? Okay. So here I want to show one example. Okay. So So we find that there are some other compatibility condition. Remember, this is still in single crystal. In addition to middle eigenvalue of the stretch tensor equals to 1 cofactor condition. That is, if we have twin laminae, and this twin laminae satisfies some further condition, that is the cofactor condition, and then we find the material can be similarly reversible, also mechanically reversible. I don't want to talk a lot about this material. So this material has been presented many times, but today I really want to present a counterexample. So we can do a lot of fabrication by adding chemical doping elements to make a lot of materials. But what if the material intrinsically incompatible? Can we save it? So we give up the material? So this is what I really want to look at. So today I would like to present a counterexample, a very incompatible copper-based alloy. And compared to those good alloy, this alloy is really bad. This alloy, we calculate the transformation stretch tensor, is middle eigenvalue is far away from 1. So we also show that this material, if we put it on the thermal cycle, this material has a huge thermal hysteresis 50. And when we just cycle 100 times, this material degrades a lot. And we can even look at the microstructure here near the grain boundary. Initially, the grain boundary is not so clear, and after some cycle, we can see the crack growth and the material fractured if we keep cycling it, and the grain boundary goes to pieces. And then we put it on the stress-induced uniaxial compression test. And before, I want to give a little bit review, how do we treat the single crystal under the stress? So suppose we have a domain, which is a pillar here. And then we have the transformation stretch tensor. In austenite, we have identity. And when we compress it, uniaxial compression, and it develops these twin laminates here. And because lambda 2 is not equal to 1, but the transformation stretch tensor still can make the twin laminate compatible with the austenite through some transition layer, and we can calculate this crystallographic equation, and we can get all the compatible all the compatible twin laminates that can form in this pillar. In this specific case, we can get 96 compatible twin laminates. And then, we put them in a set, we call it a compatible twin laminate set. And then those twins may be formed during the compression, and the minimizer is that such that minimizes the time pulse free energy minus the T dot F, that is the mechanical power. And then this is equivalent to maximize the compressive axial strain. So we actually use this max to find out exactly what twin laminates that will form under the specific loading orientation. As you can see, that this really depends on what orientation you load. Okay, so obviously the minimizers, there are some symmetry related laminates in that set. And for this specific material, we find the pair of variants that can form for orientation 101. There are several, and they maximize the compressive axial strain, and that gives the same values here. Yes.
Good question. When you have this sort of a situation where you don't have compatibility, like the invariant plane condition is not satisfied, so there is this averaging business, and so you get the twin laminate. Microscopically, do you see twin laminates, or are there dislocations there?
We see twin laminates instead of dislocations.
Okay.
Actually, that also showed in the previous slides in the single crystal copper aluminum nickel. We see like twin laminates branching into austenite.
Yeah, but really near. Okay.
Nobody really look at in the transition layer. That's
that's what I'm asking. That's what I'm asking.
That's very hard experimentally. Yeah, but macroscopically we do see the
Yeah. Okay. Go ahead.
And we also show in another orientation the minimizer obviously changes because the loading direction changes, and that corresponds to a bigger axial strain. And what we do is that we actually loaded the specific the micropillar, and we fabricate micropillar along 101 orientation and 4512 orientation. And we find the first cycle transformation axial compressive strain exactly match this value. And for this one, it exactly match this value for the first cycle. And then we load it repeatedly to drive the phase transformation for many times. And we find the mechanical reversibility actually are quite different in the same composition, same material. So here, if we load it differently here, the induced stress is 600 MPa, something like that, and it can reversibly transform back and forth up to 10K cycle. And for this one, actually it breaks after several hundred cycles. And as you can see, the timing for this is actually smaller than that. And we conjecture that, I'm not sure if this is a good conjecture. We think the loss of the reversibility is because this kind of formation of the outside martensite inhibit plane. And if we compress it, there's a resolved shear stress. And this resolved shear stress can be calculated like that. And this resolved shear stress, people call it Schmidt factor. If this is bigger, that means if you compress it, the resolved shear is bigger. And that if there's like defects, like dislocations, for example, that will slip and make this material crack. That's our conjecture. Again, no experimental proof for that. We just find a coincidence, like the Schmidt factor is smaller, the reversibility is better, the Schmidt factor is bigger, the reversibility is worse. And then let's compare this material. So this material, the thermal, here is the thermal reversibility versus the mechanical reversibility, and we find that mechanical reversibility depends on what orientation you load. And what about the grain boundary? If we have grain boundary in the material, how would we treat this material? So, first of all, let's do a very stupid and brutal minimizing of that total free energy. So if we have all the compatible twin laminates in this set, and we find which one can minimize that energy for one orientation, and which one can minimize for the other orientation if we have a bicrystal with the grain boundary inside. And of course, we can use EBSD or some other experimental approach to map the orientation of one grain relative to the other by some rotation matrix. So we know this. And then we find it doesn't fit. Okay, so if this one is a good twin laminate in this side, and this one is a good twin laminate in this side, doesn't fit. Okay, then in addition to crystallographic compatibility that we discussed a lot in previous years, it requires a tier 2 compatibility that really need to consider the grain boundary. So here, our model is that, so if we have twin laminate IJ and KL form near the grain boundary in this kind of micropillar, and they have to satisfy the crystallographic equation, and they have to be compatible with the austenite through some transition layer if this is not a very nice material. Okay. So then both twin pairs in their own grains should satisfy this. This is designed by us, and this is purely heuristic. It's just by observation. So we think, okay, if you have some grain boundary, we first want to probably minimize the area jump. That is the cofactor of the difference of the deformation from both sides. And then if you have two orthogonal in-plane vectors, we want to minimize the extension from left side to right side. That is this. Okay. So we just very, very naively design this. And then among all compatible twin laminates, we just find the minimum values of this correspond to what twin laminates on right hand side and what the twin laminates on the other hand side. So this is the result. So instead of those type of things for the single crystal crystallographic compatibility, we find different twin laminate, which is 5, 4, 4, 6 that satisfy this, make it minimum, and that corresponds to this metric in the very small values. It's not 0, so that means still there is some misfit, but the misfit has been minimized. And here I want to give some comparison between values of the crystallographic compatibility and this kind of, I call it tier 2 compatibility. So since this is the aerial job, so I just put a square here. So here, as you can see, they're more or less in the same level. That means here you have some like elastic transition layer that due to the not equal to 1. And here you have some like twin laminates that form to like accommodate to each other at the grain boundary, giving this kind of very small misfit. And how about the shear? Okay, so if we load it, there's still like resolve the shear from this side and resolve the shear from that side. So here we look at the spatial orientation distribution of the shear for the twin laminates for 6 and for the twin laminates for 5 in their own like orientation space, and we plot that. So we plot the orientation of the C here, and we find, okay, so for 6 twin laminate here, so if this is 4, 5, 12, which is actually GR2, and it corresponds to a lower Schmidt factor. What does it mean? That means if you have 101 loading orientation here, and it formed for 6 kind of twin laminate with this kind of plane, if you have this kind of dislocation, it can drive this dislocation move, but it cannot move further because the Schmidt factor becomes smaller. And the same way here, so if you have 4 by 12 loading direction in this grain, and if you have Schmidt factor, which is 0.3 something, and if you want to move along this transition layer, it lower at the other side. So if you want to go this kind of interface, this just prevent the dislocation move across each other. We call it like interlock something. So again, this is our conjecture. We think this probably the way can really improve the material reversibility under the stress. And what we do is we find a grain boundary and we make a bicrystal pillar. We hope half of it is one grain and we hope another is another grain. And then, okay, so the middle here, the middle row corresponds to the bicrystal, and we find that this material is very interesting. The residual strain, the permanent strain is the least. That means if we load it up and down, although the total transformability is sacrificed because we didn't really maximize the axial strain, but the reversibility has been much enhanced due to this kind of accommodation within each other.